In this video, we're going to talk about Newton's method, which is a tool for estimating the roots of a function using calculus. So we've talked about solving equations in Sage before using either the find root command or the solve command. So the purpose of this lab is not really to give us a new method for doing that. Those commands are much better than Newton's method, but to give you some idea of how a computer or a calculator can solve equations numerically. So it's sort of just see how calculus can be used for something that's not directly a calculus thing. Estimating roots, that's really a pre-calculus matter, but calculus can provide some insight into that. So anyway, the basic idea of Newton's method is that a function, at least a function that's differentiable, is close to its tangent lines, at least near the point of tangency. So if we know the root of the tangent line, which is easy to find, then we can, we'll assume that the root of a function is somewhere close to that. So that's the basic idea. Let's look at an example. Let's say I want to estimate the roots of this quadratic function, and of course we don't need Newton's method to find roots of quadratic functions. We could use the quadratic formula or factoring or whatever, but let's just do this as an example. Here's a graph of the function. You can see that it has, like we expect, two x-intercepts or roots or zeros, whichever words you like. There's one here somewhere around -2.5, and there's this one here, it's around 1/2. So let's look at the one near x equals 1/2. So the idea is to find a tangent line for this function, and of course to get a tangent line you need a point of tangency. So we're going to go ahead and use this 1/2 as the x-coordinate of our point of tangency. I got that half just by estimating the root from a graph. That's one of the disadvantages of Newton's method, is you have to have an idea of where to start, and we're going to do that graphically. So from the graph we see the answer somewhere near 1/2, so I'm going to build a tangent line based off of x equals 1/2. Here's the formula for our tangent line. So x sub 0 in this example will be 1/2, and when you calculate the function value there, we'll need to calculate the slope from the derivative, and then we'll just plug them in. So here's the calculations in Sage. There's the definition of the function f. Then I calculated the derivative. Then I found the tangent line. It's just this formula up here with 1/2 in the place of x sub 0. And f prime I called df as I normally do. That's the derivative. Here's the answer. I had it printed out. That's the tangent line. And here's the graph. I zoomed in on the graph of this function. So here's the point of tangency at x equals 1/2. That's that black dot. And you can see that the x-intercept here of the function is not exactly 1/2. It looks like it's 0.4, who knows, 0.41, 0.42. And you can also see that the x-intercept of the tangent line in the red line is very close to the x-intercept of the function in blue. So they cross pretty close together. So their tangent line is going to give us a decent approximation for the root or x-intercept of the function. So let's go ahead and find where the tangent line crosses the x-axis. So this is the equation for the tangent line that Sage gave us. We want to see where that crosses the x-axis, so we're going to plug in y equals 0 and solve for x. So here's the algebra, and this is the answer. 0.416 repeating is where the tangent line crosses the x-axis. I'm going to zoom in again. So here's our point of tangency, 1/2. Here's the x-intercept of the tangent line, the 0.416 repeating. Here's the x-intercept of the actual function, which is a little bit less than that. They're not too far away. It's not exactly the same, but it's a good approximation. Now, Newton's idea was, okay, well, that's fine. This is a good approximation to start with. Can I make this approximation better? And Newton said, yes, why don't we use this approximation, the 5/12 here, use that as the basis for a new tangent line, and find the x-intercept of that new tangent line and just repeat the process. So that's what we're going to do. We're going to have a new tangent line based on 5/12, where 5/12 was the x-intercept of our previous tangent line. Alright, so same process I did before. I just replaced all the halves in the previous tangent line with 5/12. Okay, So here's my new tangent line. Here's the graph. I've zoomed in some more, and this is the 5/12, the 0.416 repeating. That's the new point of tangency. This red dashed line is my tangent line. It's right on top of the blue function, at least on this window, and you can see that these are very close together again. So let's go ahead and find the root of the tangent line. So set y equal to 0 in the tangent line formula. This is the tangent line equation I got from Sage, and this is what I get, 169 over 408, which is roughly 0.414. Now here is the exact answer. It's the square root of 2 minus 1 is the one that I'm looking at, which is roughly 0.414214. Oop, let's see if we can get both of them. So this is my approximation based on the second tangent line. This is an approximation based on the exact answer. So I just rounded to 6 decimal places. And that's pretty good. In fact, if you subtract the two, take our estimate and subtract the exact answer, I rounded however many decimal places this is, you can see that they're very close together. The percent error here is roughly 0.0005%. So very good estimate with only 2 tangent lines. If I want to improve my estimate even more, I can just repeat the process again. So use the x-intercept from my second tangent line as the basis for a new tangent line. Make that our new point of tangency, and then you would find the x-intercept of that new tangent line and keep going as far as you want. And you can see that there's a lot of repetition of the same steps over and over. This lends itself to doing it on the computer and just looping it around. Now before we set up the algorithm for the computer to use, I will have a couple comments. One, we have to start this whole process somewhere. We needed a point of tangency to begin with. The computer can't choose that. So we used a half in that example we did, and that was based on just eyeballing it from the graph. Now the closer that initial guess is to the actual root, the faster Newton's method will give us a good answer. If that initial guess is chosen poorly, Newton's method might actually fail. It might not get to the actual root, or it might take 1,000 repetitions to get there. So you have to be careful in choosing this initial guess. Also, Newton's method only estimates one root at a time. So if you choose a different point of tangency, you might end up at a different root. In this example we just did, the function had 2 roots. One was a negative 2.5, and one was the positive 0.5. So if we chose a point of tangency that had, say, x equals -2, we probably would have found that other root. And if you want to find all the roots, then you have to repeat Newton's method for every single root there is. It only does one at a time. All right, well, let's go ahead and develop an algorithm, generalize Newton's method, so the computer can do it all for us. So if you have a function that has at least one root, of course, if there are no roots, then this is not going to work out. So it needs to cross the x-axis at least once. First step is to get a ballpark estimate for the root, so that we can have the x-coordinate of that ballpark estimate is going to be our x-coordinate for the first point of tangency. We're going to call that initial estimate x sub 0, and we're going to estimate that graphically. So we're going to graph the thing and just eyeball it from the graph. It doesn't have to be a great estimate, just need to have a decent estimate of our root. Okay, once we have that ballpark guess, x sub 0, we're going to make a tangent line based on x sub 0. There it is. We're going to find the x-intercept of that tangent line by setting it equal to 0 and now solving for x. So here's the algebra steps. Solve for x, and then we'll simplify a little bit and we get this. The x-intercept of our tangent line is x sub 0 minus the function value there divided by the derivative there. I'm going to call that x sub 1. Okay, that root of the tangent line is x sub 1. X sub 1 is going to be the basis for a new tangent line. So we're going to make a tangent line based on x sub 1, and we're going to find out where that new tangent line crosses the x-axis. Well, what we're going to do is repeat this whole process. You're going to replace all these zeros with ones, all these zeros with ones. The algebra is the same. It's identical. The numbers will be different, but the algebra process is the same. Replace all these zeros with ones, and what you get is this thing, which we'll call x sub 2, is going to be the x-intercept of the second tangent line. And it's going to be exactly, looks just like this one, except I replace all the zeros with 1s, and I replace the 1 with 2. The index just goes up by 1. And then you repeat. Same process again. You take x sub 2 and you run it through that process. What's going to happen? All these 1s will get changed to 2, and this will be x sub 3. That'll be the x-intercept of our third tangent line, and so on. If you've repeated the process n times, then you take your nth estimate based on your nth tangent line, you plug it into this formula, and that gives you your n plus 1 estimate. This is the formula that makes Newton's method work. Okay, so let's go ahead and lay it out on the computer. I'm going to use this as my example function, though you could use whatever function you like. So first off, I need to define the function in Sage, so there I define the function. Second, I need to choose an initial value, the x sub 0, place to start. I'm going to do that graphically. So I graph the function, and you might have to adjust your plot window depending on the function you're dealing with. So here I can see, what is this? This is about a half again. This is where it crosses the x-axis. So my initial guess is going to be x equals a half. Now I don't want to bother with subscripts in Sage. I could do it, but I don't really care about keeping track of all the individual estimates. So I'm going to, instead of using x sub 0, x sub 1, x sub 2, etc., I'm just going to use the letter r for root. And as I go through the process, I'm just going to take the old r and replace it with my new estimate. So r is just going to change as I run through there. So this is my initial guess. I guess the root is close to a half. I need to decide how many times I want to repeat this process. So I'm going to repeat it 10 times. I'm going to call n that's going to be my name for the number of repetitions. So 10 repetitions. I need to find the tangent line. Sorry, I don't need to find the tangent line. I need to find the derivative, because that's part of the formula. Remember, the formula is the old estimate minus the function value divided by the derivative at that old estimate. So I need the derivative. So I call my derivative df as usual. Now we're ready to iterate Newton's method. I'm going to use a for loop. So here's how a for loop looks in Sage. Type the word for. I need some sort of index for my for loop. I'm going to call this index I. It doesn't really matter here. We don't use the index for anything. It just needs to run through n. Range n is a Sage command produces a list of n integers. It's actually 0 through n minus 1. But all this for loop does is repeat the following n times. That's what this says. And then a for loop, you need a colon at the end, and then everything that's indented after that for line is going to be included in this for loop. It's going to get repeated n times. This indent is necessary. It's not just for looks. You have to indent this. Sometimes students will copy this and they'll lose this indent and it won't work. Okay, make sure you hit tab, and so this is indented over. All right. So I'm going to go ahead and use this n command to convert to decimals. If you don't do that, then Sage will try to keep exact values, and it will run slower, especially for some function. If you have trig functions involved or log functions, then it does slow down quite a bit. So I'm going to convert to decimal. Here's my formula from above. Old estimate minus the function value divided by the derivative. That's the formula we developed for Newton's method. I'm going to convert that to a decimal with 30 digits here. That's what this digits equals 30 does. That's going to be my new estimate. So my root gets replaced with a new estimate based on this calculation. This line is just going to print out that new estimate so that I can see them in a list. Okay, so remember I started out with a half. This first output here is the x-intercept of the first tangent line that's based on x equals a half. This is the x-intercept of the second tangent line, and so on. The last one is my best estimate. What I hope to see as I look down this list is that these numbers should stabilize. If these numbers are flopping all over the place, then something's not quite right. Probably my initial guess was not any good. Or I haven't done enough repetitions. As you can see here, you get down to this level. From here on to, I got 30 decimals places here. From here on, they're all the same. that's good evidence that I've gotten the right answer. Okay, so this is my best estimate for the x-intercept of this function. Now, just for the sake of comparison, here is the exact answer. There is a cubic formula. This is a cubic polynomial, the original function, and there's a formula for solving those. Though I actually just use Sage to solve it, but this is the exact answer. It's kind of a mess. Here is 15 decimal places of that exact answer. Here's 15 decimal places of my approximation, and oh, they match. So, and that, remember, only took 5 repetitions to get there. Okay, 6 through 10 were the same answer. To 30 decimal places, they all agree to 15. So it really only took 5 repetitions to get 15 decimal places of accuracy here. A couple side notes before we do another example. One, you can use Newton's method to find complex roots. So if you're looking for a root that's not a real number, okay, you're not going to see that on the graph, of course, because the graph is only going to have real numbers. But if you want a complex number, you can find them with Newton's method. If you start with a complex guess, then you'll get complex answers that come down. Of course, that's harder to know where to start because you can't see them on the graph. Second note, I mentioned before, Newton's method doesn't always work. If your initial guess is bad, then everything will fail. An obvious example is if your initial guess is a local minimum or a local maximum. In that case, you get a horizontal tangent line. And a horizontal tangent line has no roots. So you end up with, your method breaks down. You don't have a new x value to make a new tangent line because you have no x-intercepts. If the function has a limited domain, then it's possible that the tangent line might cross the x-axis outside the domain of the function. And when that happens, you can't continue the process. It breaks down. So you have to be fairly careful choosing your initial guess. It doesn't have to be perfect, but there are some requirements. Here's an example of a poor choice of initial guess. So here's the function is x squared minus 2, this parabola. I chose my initial guess of 0.05. Now when I look at this, the actual answer, this is about 1.5 is about where the root actually is. The answer is actually the square root of 2, so it's about 1.41. Anyway, I purposely chose a bad initial guess here, 0.05, really close to this minimum. If I chose the local minimum itself, x equals 0, I would have gotten a horizontal tangent line and nothing would happen. Here, I chose an x value close to that local minimum. And what happens, you don't get a horizontal tangent line, but you get a fairly flat one, so its x-intercept is way out here. The actual answer is like 1.5, and I got something near 20 as my second guess here. Now, Newton's method will get back to the right answer. It's just going to take a little longer. In the last example, after 5 repetitions, we were already there. Here it takes a little more. So here's my first estimate, which is terrible, and it slowly works its way back. Okay, this is, if I make a new tangent line at 20, then it crosses the axis at 10. And if I make a new tangent line at 10, it crosses the axis at 5, and then 2, and so on. And eventually you get down. Here's the 10th one. And here is the actual answer, which is square root of 2, to the same number of decimal places. They agree, but it took all 10 repetitions to get there. So it just took a little longer. But it did work out eventually. Here's another example of a poor choice of initial guess. The function is the natural log of 3x, and that function has a limited domain. At least if you want a real number to come out, you need the input to be positive. So 3x needs to be positive to be in the domain of this function. I looked at the graph, but I chose a bad initial guess. I based my tangent line on x equals 1. And you can see the actual root was this like 0.35 or something like that. So 1 was a bad guess. Here's the tangent line. The tangent line crosses the x-axis over here in negative land, and you're kind of trying to make a tangent line based on this x value. And the function isn't over there, so there is no tangent line. Now, if you try out Newton's method in Sage, it will work, sort of. It will give you complex numbers. And that's because the definition of natural log can be extended to accept negative inputs if you allow it to give complex numbers out. And that's what's happened here. in this case, it actually comes back to a fairly reasonable answer here, because, I don't know if you noticed this, see this scientific notation, e minus 8? This is actually a really small number. This is basically rounding error, and it's giving you the answer of 0.333333 here, which is actually not too bad. If you look at this thing, a third is the right answer, right? Put in a third here, you'll get the natural log of 1, which is 0. So the correct answer is a third, and you do kind of get there, but don't count on that. Okay, so that was developing the whole method and the theory. Let me finally put it all together in one chunk for you to use for your assignment. So when you get to your assignment to do Newton's method, copy and paste this whole chunk. Make sure when you copy and paste you don't lose this indent here. Okay, remember this indent is necessary to make it work. So you can change the function f to whatever it is on your assignment, hit run, and look at the graph. You might have to adjust the plot window here, probably on your assignment, and you might not have to, but adjust it if you need to. Based on the graph, choose an initial guess for one of the roots. This one has 2 roots, which we'll have to repeat Newton's method twice to get them both, but choose one of them. So here's one's like 1.5, roughly. And so then go up here and based on the graph, change the r. You can leave n as 10. You don't need to change that. The rest of it will stay the same. The only reason to change any of this is if you decide to change this f, which you don't need to change f, just leave it f and then it'll all work. If you do change this though, if you decide to call this g or h or something, you'll have to change all of the rest of them. Okay, so change the function, hit run, look at the graph, change r, hit run, that's it. Here's our answer. And the only reason to do anything else is if your initial guess was bad. If you don't like the output, you can change your initial guess and try again. Okay, I'm going to repeat it for the second root. So I saw before the second root was roughly minus 1.5, so I changed r and I ran it again, and here's my estimate for the second root. Okay, you can also use Newton's method to find the point of intersection of 2 functions. So we got 2 functions, I'll call them f1 and f2. I want to know where they cross. The idea is to define a new function, which I'll call f. F is going to be f1 minus f2. I'm going to find the roots of f. That is, where is f equal to 0? If f equals 0, that means f1 and f2 are equal to each other. That's how f1 minus f2 can be 0. And that means that they cross there. So the x coordinates of the points of intersection of f1 and f2 are the roots of this new function f. Okay, so here's an example. Here's my first function. Here's my second function. I want to see where they cross in this window between 0 and pi. So I define the 2 functions, f1, here's f2. I define the new function f, which is f1 minus f2. I plot this new function, and in this example I only care about 0 to pi, so I just plotted from 0 to pi. I can see that there's 2 x-intercepts here. There's this one, which is like, what is that, close to 0.2, and there's this one that's actually pretty close to pi, like 3.1 something. Alright, let's find this first one. So I changed my r to 0.2, and here's what comes out. So this is the x-coordinate where those 2 functions cross. Now, the point of intersection is not just x. It's actually an ordered pair, x and y. So to find the y-coordinate, I need to plug this into one of the functions. I'm going to go ahead and plug it into both of them, because that's a way to kind of check and make sure I didn't do anything wrong, because if they're the same, then it's working. That's the whole point. These y-coordinates are supposed to be the same. So I just copied and pasted this answer into f1 and f2. I converted to decimal with 30 digits, and I got the same answer. So great. It looks like this is our point of intersection. So this thing I got from Newton's method is the x-coordinate. The answer I got here by plugging it into the function is the y-coordinate. Now the second root is a little bit hard to get in Sage, because Sage does not allow fractional powers of negative numbers. So here I have a 1/3 power. That's how I do the cube root. in Sage. And if x is bigger than pi, then sign is negative. And so you get a negative number raised to a 1/3 power, which is not allowed in Sage. Even though since 3 is odd, this is an odd root, the number is perfectly well defined, but they haven't programmed it yet in Sage, I guess. So anyway, you got to be really careful with your initial guess. Otherwise, you end up getting outside the domain. You go past pi and it doesn't work in Sage. So I had to fiddle around with this a while till I got this approximation for R. So I just had to zoom in and really get a good approximation. And here is what it gave me. All right, so this is my best answer for the x-intercept, and I plugged it in, and here is the y-coordinate where they cross. So this is our second point of intersection. It's very close to pi, but not quite exactly. Just for fun, I made a graph. I'm not going to ask, I can't remember if I asked you to do this on the assignment or not, but I felt like graphing them just to see. So I put a dot at those 2 points of intersection. I added those points onto my graph just so I could see that yes, indeed, those are the points where they cross. And that's Newton's method.